Okay, hello everybody. In this module, we're going to be reviewing the gain margin and the phase margin for discrete time systems. Now, the full coverage of the gain margin and the phase margin will require the study of the Nyquist stability, which is beyond the scope of what we're trying to cover. Nevertheless, an understanding of the gain margin and their usage in determining the stability of the system is needed. So therefore, we're going to review what the gain margin and phase margin mean, and we're going to do an example to help you fully understand what they mean and how they help us determine the stability of a system. So let's say here we have a system G of S, and we have a unity feedback. We have the output that is fed back to the input, and we took G of S. We plotted the Bode plots of the magnitude of G of S, and we plotted the phase of G of S. So this is omega, G of omega, J omega, and the phase of G of J omega. So I got a plot of the magnitude as omega changes, a plot of the phase as omega changes of the open loop transfer function. Now what I'm going to do is I'm going to come to where this phase becomes 180 degrees. So at this frequency here, omega gm, I'm going to extend it all the way here. This is omega gm. I'm going to call this the gain margin. And I'm going to come where this magnitude becomes 0. I'm going to extend it, and I'm going to call this omega phase margin. And this magnitude here between 180 and where the curve is, I'm going to call it the phase margin. So from this graph, I mean, if you look at the Bode plots, you can easily determine the gain margin and phase margin, where when the phase is equal to 180 degrees, that will tell me what the gain margin is. So this is defined as the gain margin, where the magnitude is equal to 0. This phase from 180 to the curve is the phase margin. Now, what is the significance of these, and how do they help me determine the stability of the system? So let's say that I come to this system here, and I'm going to take a sinusoidal signal that I'm going to apply to this system. The frequency of this sinusoidal signal is omega gm, this frequency here. Now what's going to happen, this signal is going to go through the system, and then I'm going to generate an output. I'm going to take this output, I'm going to feed it back, it's going to get subtracted from the input, and so on. Now this signal that I'm going to get at the output that I'm feeding back, it can go through one of three things. One, it can either get amplified by G of S, or it can maintain its magnitude, or it can get attenuated. So let's see what happens in each case. So what we're going to do, we're going to apply this sinusoidal signal, and then after I start getting an output, I'm going to remove this sinusoidal signal. I'm going to turn off my input. So therefore, the only signal that's coming to the system is the signal that's coming from the output. Now if the gain of the forward loop G of S is less than 1, then the signal is going to continuously diminish and die out, and therefore the output is going to go to 0. Now if the gain of G of S at that frequency is equal to 1, then this signal is going to just go here through G of S, and is going to keep going back and forth, and therefore I'm going to have an oscillation at the output with constant amplitude. Now the third case, if the gain of the system is greater than 1, then this signal, when it goes to G of S, is going to get amplified, and it's keep getting amplified, and therefore I'm going to get an output that grows with time, and therefore the system unstable. So again, we have three cases. We have a case of what could happen, three cases. we have a case when the gain is less than 0. So the gain g of j omega gm is less than 0. And in this case, the gain margin, we're going to have a positive gain margin. And in this case, the system is stable. The second case is I'm going to have g of j omega gm that is greater than 0. And in this case, the gain margin will be negative. And in this case, the system is unstable. The third case is the gain g of j omega gm is equal to 1. And therefore, in this case, we're going to have a system that is marginally stable. In this case, the gain margin is equal to 0. Of course, the gain margin is measured in dB. So 0 dB, it means it's just a 1. Okay. Is this hopefully this is gives you an insight of what the gain margin and how it relates to the stability. A positive gain margin, like I have in this graph, we measure the margin from here up. It is positive, therefore we have a positive margin. The system is stable. The gain of the system is going to be less than 0, and the system is stable. I could have a system that has a negative gain margin. If this curve was having this shape here, this will have a negative gain margin. So this is a negative gain margin, this is a positive gain margin. Or I could have the system such that it has a 0 gain margin. This will be like this curve that I have in red here. There's a 0 gain margin. And you can see how this gain margin relates to the stability of the system. Okay. Now again, similar to how we apply the phase and gain margin in continuous time system, we can apply it to discrete time system. So if we have a system here where we have a feed forward loop gain, and we have a plant, and we have a feedback loop, the open loop transfer function is defined. Open loop transfer function, if I open the loop here and I look at the transfer function going all the way like this, then the open loop transfer function is HFF multiplied by HFB multiplied by G of S. We call this the open loop transfer function. Now this signal here that we're feeding back, if we call it B of S, then the transfer function between B of S over E of S is equal to HFF multiplied by HFB multiplied by G of S. Now if I take the body magnitude of B of j omega over E of j omega, and the phase of B of j omega over E of j omega of the open loop transfer function, that will give me the Bode plots that we need to determine the gain margin and the phase margin. So in this case, if I were to plot for a system, again, the magnitude and the phase of all these transfer functions, and if I get a graph that looks something like this, then to determine the gain margin, I'm going to come to the phase and see where the phase is 180 degrees. At that frequency, I'm going to measure from here to the 0. This is 0 dB. And this is going to give me the gain margin. In this case, the gain margin is 18. Now what this means, what does this 18 means? It means I have a cushion against the system becoming unstable of 18 dB. If the system had a curve that looks something like this here, then it will be marginally stable. I have 18 dB before I reach that curve there. So this is what the gain margin means. Similarly, I'm going to see where I'm crossing the axis here, at 0 dB. This is going to define the phase margin, and I'm going to measure from negative 180 to the curve, and this will give me the phase margin. So in this case, if this point is negative 90, then the phase margin is 90 degrees from here to here. And again, if this was, for instance, negative 18 dB, then my gain margin is 18 dB. I know there is negative and positive, and this might be a little bit confusing. Nevertheless, remember, the gain margin is measured from here up. If I am below the 0, then I have a positive gain margin. The phase margin is measured from the negative 80 to the point when the magnitude is 0. Okay, so we defined the gain margin frequency, the frequency at which the gain is negative 180, the phase margin frequency, omega pm, the frequency at which the magnitude is 0 dB, the phase margin, the amount by which the phase of B over E exceeds the negative 180 when the magnitude is equal to 0, and the gain margin, the factor in dB by which the gain must be changed so that B over E is equal to 0 dB when the phase is equal to negative 180. Okay, so this is used in studying the continuous time systems. Now what we're gonna do is we're gonna take this and apply it to discrete time system. Okay. And before we do that, okay, so we talked about this, the gain margin. If I have a small gain margin, it means I have, so in this example here, I have a gain margin, or in this note here, I have a gain margin that is equal to a 3 dB. What this means, the system is stable because the gain margin is positive. However, I have very small cushion against becoming unstable. So therefore, I want my gain margin to be as large as possible because that is a cushion against becoming unstable. So we want usually to have a gain margin that is greater than dB and a phase margin that is greater than 30 degrees. Now extending the gain margin and phase margin to the discrete time systems can be done, but in order to do that, we have to use the W plane, and therefore we have to do the bilinear transformation on the transfer function before we plot the Bode plots of the system. Okay, so let's do an example. So we have a system here, input k g of z. This is a discrete time system. G of z is given by this transfer function. We can calculate y over e of z, and this is equal to k multiplied by g of z. So this is the transfer function between e and y of z, which is this. Okay, so we want to calculate y of w over e of w. Now this w, it's not omega, it's w. So therefore, we're going to have to calculate or transform the z to the w plane. So I have y of z over e of z. I'm going to take z and replace it with 1 plus t over 2w divided by 1 minus t over 2w. And we are given t is equal to 0.1 seconds. So if I do that, if I plug in for z with 1 plus 0.1 over 2 multiplied by w over 1 minus 0.1 divided by 2 multiplied by w, I'm going to get y of w over e of w, and this is the transfer function that I'm going to be getting. This is w and this is w. Now I can apply Bode plots to determine the gain margin and the phase margin. So if I come here and plot the phase margin, and if I plot the Bode plots, the magnitude and the phase, in this case, when the phase is 180 degrees, it's at this frequency, so therefore this is my gain margin. And when the magnitude is 0, this is my phase margin. And to do that in MATLAB, I have the commands here, but we're going to get the discrete time representation of the continuous time system. So this is, in this case, we have this is the continuous time system. NS, the numerator, denominator. We're going to transfer. Now this, I'm using Octave, so therefore it needs to use a transfer function to create a system. If you're using MATLAB, you don't need the TF, the transfer function. You can just C to D, NS, comma DS. Okay, so we're going to get NZ, DZ, and then this will give me G of Z. This H of Z is G of Z. And then I can transform this to the W plane by doing D to C, HZ, TUS, TN. And therefore, this will give me the HW, and then I can use that to plot the Bode plots. So Bode plots is going to be using HW that I calculated here, and the frequency that I can generate from here, and this will give me magnitude and phase and the frequency W. And then I can run margin, magnitude, phase of W. It will generate these two graphs for me, and it will also give me the value of the gain margin and the phase margin. Okay. Thank you, everybody.